Isoleucine is one of the 20 amino acids that's used to make a protein within the human body. Just like every other amino acid, there's a central carbon, the chiral carbon, the alpha carbon, that has 4 different constituents or 4 different attachments on it. Every amino acid is going to have a carboxylic acid where you have a carbon with 2 oxygens and a hydrogen. It's going to have an amino group where you have a nitrogen with 3 hydrogens attached to it. This nitrogen should only have 3 attachments, not 4. So because it's carrying this extra hydrogen, this is going to carry a charge of +1. And then the amino acid is always going to have a hydrogen directly attached to that chiral carbon. And then that amino acid is going to have an R group. In the case of isoleucine, this is the R group. It's a whole bunch of just carbons and hydrogens. At the lowest pH, or the place where the environment has all kinds of extra hydrogens to be able to give up, the most protonated form, or everywhere you can have a hydrogen, you're going to have a hydrogen, is what the amino acid is going to look like. As the pH goes up, which means you start losing hydrogens from the environment, and this molecule is going to have to give up some of its hydrogens to the environment to balance things out, the first hydrogen that's going to be lost from this amino acid is going to be lost from the carboxylic acid. And when that carboxylic acid loses its extra hydrogen, this oxygen is going to have a lone pair of electrons, and now it's going to carry a charge of -1. That's going to happen at a pH of about 2.3. This nitrogen down here still carries a charge of +1, so you've got a +1 here, and you've got a -1 here, which balance out to an overall charge of 0. This is called a zwitterion, when you have a +1 and a -1, so there are formal charges on the molecule, but the overall molecule itself carries a charge of 0. Now you keep going up, increasing the pH. Eventually, this nitrogen is also going to start to lose one of its hydrogens. But that's not going to happen until a pH of about 9.8. At that point, this hydrogen is going to go back to its neutral charge that it always wanted to be. And so now you're going to have this -1 still from this extra lone pair of electrons, and this is going to be at 0. So overall, this is going to carry a charge of -1, above a pH of 9.8. This R group is just carbons and hydrogens, so it's never going to lose these hydrogens no matter what the pH is going to be. But the pH of the human body is about 7.4, which is called the physiologic pH. And at the physiologic pH, that's way below that 9.8 that I was talking about where this nitrogen loses. So at 7.4, this nitrogen is still going to have its hydrogen, but this carboxylic acid is going to have lost its hydrogen. So you're going to have a -1 here and a +1 here. So the human body's form of isoleucine is going to be the zwitterionic form, or it's going to carry an overall charge of 0. Now let's talk about the R group. Isoleucine is literally an isomer of leucine, aka it's going to just have a different chemical structure than what leucine has. So if you look here, this is a carbon that's going to be directly attached back to this amino acid. And there's going to be 1 carbon attachment here, 1 carbon attachment here, another carbon attachment up here, and then 1 hydrogen attachment. Because this is not just a direct chain, all of these carbons are not just directly going off of the amino acid. This is considered a branched chain amino acid. And in the case of leucine, instead of this carbon being the one that has this extra carbon attached to it, they're just going to switch places. So you're going to have a hydrogen that was here is now going to go here, and it's the second carbon off of the chain that's still branched. Either way, leucine and isoleucine, you didn't change the chemical formula of them at all, just the way that the structure is arranged. This is strictly carbons and hydrogens, which are all nonpolar bonds. And so because these are all nonpolar bonds, there's equal sharing of electrons between the carbons and hydrogens everywhere. This is also not going to be able to do any type of hydrogen bonding because there's no point in which polarity occurs to enable it to bind to another molecule that's polar. So this R group is going to be both nonpolar and hydrophobic. Any branched chain amino acid, this is too bulky, too awkward for your body to be able to make inside of it. You have to eat it in order for it to show up in your human body. So isoleucine is an essential amino acid. You have to eat it in order to make it in your human body. But you can use isoleucine to make a whole lot of other things in the human body, including glucose and lipids or fats or ketone bodies. So this is considered both a glucogenic, or can make glucose amino acid, as well as a ketogenic, or can make ketone bodies, which make fatty acids, a ketogenic amino acid.